Well, let's get started with the video and the stream. Thank you for joining us again on this fine Saturday afternoon. If you're enjoying what we're doing, definitely like, subscribe, hit that bell notification to be informed of when we drop new videos on YouTube. If you get a chance, check out the Twitch stream. So far, we've been consistent, at least with this video series from Breadboard to Market. Saturday and Sunday at 2 p.m., Monday, Wednesday, and Fridays at 6 p.m. The reason I'm doing so many videos and streams for this series is there's a lot to cover. And also, I really want to get this product built and at least start testing and start developing with it. Because I could use something like this in some of my testing and other projects. So, with the last video, we left off on writing up the test plan because we're still waiting on PC boards. And I just checked my order status with JLC PCB. Looks like the actual manufacturing is done. So they just pretty much have to get put on the slow boat across the pond and arrive here. Necessarily won't be a slow boat. I think I chose UPS. So hopefully it'll be within a week arrival, as long as it doesn't get snarled up in customs, because we all know how things are going now. So those will be hopefully here within a week, and maybe we can start doing some building, getting the boards built and moving forward from there. At least the first pilot board. So with the test plan, I went ahead and added the test plan information for the control inputs. Again, it was just pretty much a mimic of the limit switch inputs. I just had to change some of the wording around. I think I see something I need to fix right there. No, nothing I need to fix. So it's pretty much just an exact duplicate. Updated the test log, so everything there is fine. So many things going on. So now we're going to look at the USB UART interface. And we're going to kind of write some similar wording for it. The reason is we want to definitely check for shorts. Is this guy has some really fine pitch connectors, which can easily solder bridge. And then the main IC, the actual bridge chip, is a VFQN chip, and all the pads are on the bottoms and really fine pitch, so you can also develop solder bridges under there. So we want to check for all of that, and that's what we'll do our best to catch off of that through these different various test points. So one of the most important things we want to check first out of this circuit is right here. We want to test point 24 and 25. That's your V bus. So that'd be your 5 volts coming in from your USB connector to ground. We want to make sure that is definitely above 5K. So finding all my stuff when my icons like to do this weird thing. So annoying. So what we're going to do is we're going to kind of come up here and find one that we are kind of wrote. We definitely want to be around 5K. I mean, that's fine. We'll fix that. We'll change that to 5K. This way the language stays consistent. Check between 24 and 25. 24 and 25. V bus. Greater than 5K. Okay. So we want to make sure we don't have a direct short on the V bus line, because if we do, then we've got a problem. And that's, like I said, that's our 5-volt line coming in from the USB port. And we definitely do not want to short in there. 24 and 25. Yeah, and all this is before we even decide to apply power to the board. Again, we want to make sure that thing's not going to smoke when we power it up. Okay, so that I would say is the most important check to do first. Now we're going to kind of check for shorts in any of these other bus lines. There aren't too many to check. And we're not going to be bouncing between them. We're just going to be checking 22 and 23. And we're going to be looking around the 1K mark, but that's fine. We'll just fix this one. One, 22, 23. Plus and minus. USB. DP. E negative. And we at least want it to be greater than 1K. Oop, not 12K. Again. So since this is going to be a lot of more the same, I'm just moving this over the other screen. I don't have to keep flipping back and forth. Because it's going to be a lot of the same, copy, paste. Basically taking what's in here and just put it in the spreadsheet in a simpler form. And that way I don't have to keep flipping back and forth. 2, 3, 1K. Again, I'm not 100% certain of these values. Not really 100% certain, but definitely it's going to be greater than or equal to 1K, and that's what we want. Or it should be. Because we're still going to be dealing with straight capacitance, because you're still going to have capacitance between the leads and things like that. So that covers the USB port. Let's kind of come down here. All right. Right here, 18 and 19. That is RTS DTR. Because those you would still have a chance for a short condition solder bridge due to the bridge chip. And then also you would have a possible bridge condition at Q7, which is going to be that little 6-pin SOT package, the dual NPN transistor package. So you could still have a bridge in there. More than likely to have a bridge on the UART bridge chip because of the package format than you are here. And this is definitely easier to diagnose and fix. You can rework this by hand if you had to. That little package if you really had to. So let's get that translated over to the spreadsheet. 18 to 19. And then we'll also, when we're done drafting a lot of this up, we'll kind of doctor up the spreadsheet a little bit, kind of add some more details to it, because there's a few other things we're going to want to do. Because while I'm on this tangent, when you want to basically attach one of these test logs to one board at a time. So if we decide we're going to say we want to run 2 boards to these tests to test batch consistencies, which we might do. we'll want one of these test logs for board 1 and a test log for board 2, and then that leads into the product serial numbers, which is why I got those smaller labels for product series, the 1 by ½ inch labels to make product serial numbers. And we'll kind of draft all that up down the road when we get closer to being done to drafting this up, because we'll need to have a plan on how we're going to generate the serial numbers. And then we're going to need to kind of track some of this stuff for the product. So little things to do, because when we go into production, we're going to have serialize the boards with the same labels, and we're going to want to be able to track which board's which for any warranty or any other things like that, so we can also keep traceability within our own processes. So only 2 more test points to check, and that is 20 and 21. And I'm going to just go and put that on the spreadsheet because it's already over here. 20, 21. And then we're going to go to VS Code. Now, is it necessary to call out what they go to? Not necessary, but that's boot and enable. Boot and enable. This helps to know. So if you want to reference a schematic and kind of figure out what they go to, the circuit that they belong to, and find the components that they tie to, it just make it a little easier. 33. So far, the VS Code, our test plan, meshes with the spreadsheet line for line as far as, the test number. So let's go back to the schematic. All right, stepper driver. Now I didn't play. I didn't put any test points on here, and that was my fault. I probably should have. But as far as the checking the motor leads, which we can check real quick, that we can check real easily for shorts. But the good thing is this is a TSOP package. It's pinned, or it's got legs on it, so a visual inspection should be more than enough. I'll just accept this as one of my mistakes. I should have put test points on all these guys, because getting to them might be a little bit more difficult. But some of them we can, if we really have to, check them here. So yeah, I'll accept this as my mistake, because we have a fan PWM driver pin. So that's another thing we'll have to address down the road, is like some sort of assembly document, like a drawing for assembling the fan that goes with this, because it's got wires and we have to crimp the terminals and hook everything up and make sure the pins, the terminals line up properly with the connector. So we'll definitely want to do a drawing for that later. We'll take care of that down the road. After we've gone through and kind of done it and kind of figured out if we need to trim the leads to a shorter length or anything. So we'll worry about that down the road. But for now, we will just focus on, I should have had, a test point off the temp sense, so we could have read its value. Again, my failure. We could contact the leads. So I'm gonna, hold on. Share with something else that I use. I picked up because these things are freaking nice. Okay. Which one are these? All right. Choose an option size. Okay. So I'm going to drag this over and show you what I picked up. So these guys, so this Tag Connect, they make some cool products, and I've been incorporating their Tag Connect headerless programming system into designs for Sanctuary software for the hardware there. And then even for my own designs, I've been incorporating the Tag Connect stuff. So, but they offer these little non-slip probe tips. They slide on, and we've got these really fine tips for making contact with really fine pitch micros and things. So these are really great. Plus they kind of are abrasive, so they'll grab hold and they won't just slide off when you're trying to take a measurement. In my opinion, well worth the cost if you intend on doing this type of work in the long run. But I'm going to kind of just really show you. So Tag Connect. I'm already here, might as well show you. So the great thing is, so basically here what they are, they're basically pogo pins. And you just have a footprint you put on the board, and you don't have to populate it with a header or anything. So your cost is in the actual cable itself, or the programmer like this. So they'll make just adapter cables for JTAG and stuff. So it's just the pogo pins and a cable that you tie into a JTAG programmer. They also have one for the pick kit, which I have for my picks. The reason I'm not using any of them for this project is because this is open source, and it's kind of open, and it's the follow along project I want people to be able to have access to without spending too much extra money. That's why I'm just using the standard breakaway headers. But in anything I build pretty much after this, even if I do showcase it on videos, I'll just use the Tag Connect. It's my preferred way of doing it. For one thing, like I said, you just buy the cable interface, the pogo interface, and you're not populating headers on your boards. So that's one part you're not paying for, one step of the assembly process, and one process during that whole thing that could go wrong or be soldered wrong or backwards. So they're really nice for that purpose. So with those little probe connectors, those little slide-on tips, I can make it a lot easier to get contacts to the legs of this guy, or even get contact to the leads of the fan connector if I really needed to. So I'm not terribly worried about that, even though I should have put test points in. I will accept that as my mistake. I think we were kind of I was trying to get through the design and I just blanked on everything. Just trying to get through this design. I rushed it and I shouldn't have. But what we'll do is we'll at least check the CN7 and make sure there's no direct shorts here. Because that's another thing, we do not want to short. So we'll check it, make sure there's no short between any of these pins and ground, because that would be bad, because this is the output for the motor. So if you've got a direct short to ground, I think this chip, if I remember the data sheet correctly, has short circuit protection. It'll detect that and it'll shut down to prevent damaging itself. But that doesn't mean it's not possible it won't damage itself. So we might as well just make sure before we even do anything. So let's go to VS Code. Let's find one of our connectors. All right, we'll just kind of grab this guy. And that's 34. So get over the spreadsheet real quick. And I need to drag down and expand my my selections here, my things. All right. Okay. So I kind of got those expanded, so I can add more if I need, as I need to. So test 34, everything's lining up. So that is CN7. Terminal 1 and 4 greater than 5K, because we also want to make, like I said, we want to make sure there's no connection between terminal any of these terminals and ground. So let me get the spreadsheet updated. 7, 1 and 4. Well, actually, no. 1 and... No, my mistake. I'm checking between ground. That does not go to ground. I'm confusing that. So we want to find a ground connection. A ground terminal that's close to this guy. So let me go... PCB editor, and we'll find a terminal that's close, a ground terminal. We could use TP7. I think that's close enough. Yeah, we'll use TP7. And TP7. There we go. And TP7. Realistically, that should be open. There should be like an infinite resistance there. It just shows an open circuit. But you definitely want to, it's either that or greater than the 5K. And we want to do this through all the rest of the terminals. 35, terminal 1, 2. Maybe 3. So I confused myself because most of these terminals do have a terminal block. Or have a connection to ground because of what they are. But this one is completely different. There we go. So that'd be terminal 2. 3. Terminal 4. All right. All right. So that checks between the terminals and ground, make sure there's no direct short. Now we want to make sure our outputs aren't shorted out. And between terminal 1 and terminal 4. Terminal 4. Just going kind of get this, and then I'll update the spreadsheet. Terminal 1, terminal 2. Terminal 3. 41. So that's between terminal 1, 2, 3, and 4. 3. Terminal 1 and 3. Make sure I'm not going to overdo myself. Terminal 2 and 3. Let's see. 1, 2, 3, 4. 1 and I'm not here. 4. 1 and 4, 2 and 4, 3 and 4. Oh, it should be 1 and 3, 2 and 3. And then 1 and 2. Yeah, let me get this ground out of here. Up a little bit. All right, so that it goes all the way down to test 43. One and 4. And 5K should be right, because it should be open due to the isolation within the driver. I can always refer to the data sheet later and for the data sheet and see what they're actually. Clean up my spreadsheet a little bit. 2 and 4. 3 and 4. And 1 and 3. One and 3. 2 and 3. 3 and then 1 and 2. All right. So. All right. So this should cover all of our resistance measurements that we should take prior to doing anything like trying to apply power to the board. That should cover all of it. So that should cover that. Now we should start applying power to the board. Copy this header. All the way down here. Initial resistance measurements. Initial board power up testing. All right. Now we're into some really, really fun stuff. So initial board power up testing. So that's 44. That bench DC. We're going to start 5 volts. Kind of go with a low voltage with a current limit of 100 milliamps. Actually, you know what? We're going to drop that a little bit. We're going to go to 50 milliamps. No, we'll do 100 because there are components on here. So what will happen is, at least with 5 volts, because we're not going to be hooking a motor to it, but with at least the 5 volt input, we'll have the 3.3 should kick on. So that power supply will kick on, and the 5 volt will. Whether or not it would be outputting directly 5 volts, that's not really a concern. What we're trying to do is make sure the power supply doesn't go into current limiting mode easily, or we don't notice any weird smells, any pops, any bings, any magic genies getting let out of the bottles, all the components, the magic electronic genies. That's what this low power test is. you have a better chance of protecting the board and catching problems and being able to do some minor rework before you smoke the entire board. Sometimes you can salvage it through this. Looks like we have another viewer in chat. Hello. Nice to see you. Great Saturday afternoon for doing electronic design and electronic projects, right? So this would be the perfect time to catch that. Even though there's no guarantee that you'll be able to save this board, but this is the best time to try to catch these problems. Yeah. Thanks for the good luck wish there. If things go right, we won't have any problems. So we're going to do here. So we have current limit of 100 milliamps. Also, the reason that it's a little higher because it should trigger these LEDs. Now, the great thing about switching power supplies is they technically can put out more current than they consume because of the switching action. Because they're only on for a few cycles and then they discharge the inductor, then they recharge the inductor. So you're only drawing current from the power supply for only half of the switching cycles, but they switch so fast. I think these guys are in the megahertz region. So they're switching so fast, so every half of those switches. Oh yeah, it is hard dealing with electronics and dealing with circuits and stuff, especially without nowadays, without having access to schematics and diagrams, bill of materials like in the old days. When I got into working on electronics, when I was a teenager, pretty much everything you bought or you could find had the schematics with the part list and everything with it. You could literally build that product over again. They were readily available. Nowadays, these companies want to swat your hand and throw you in jail for intellectual property theft. If you even want to replace a fuse in your own farm equipment or replace a spark plug. So yeah, it is getting harder to deal with this stuff because companies, and I'm going to just be blunt and honest about it, companies are getting greedy. They are. They're hiding everything behind paywalls, behind intellectual property laws. And they want to swat your hands every time you want to fix your own stuff, the stuff you paid for. So I support the right to repair. I honestly do. I think you paid for the product, you paid for the right to use it, you should have the right to fix it. And fortunately, some companies are getting on board with it. I even heard Microsoft was for their hardware. You can actually get parts from them. Again, I'm not endorsing any company. I'm not paid to endorse any of them, but there's a couple of laptop companies, like one's I think called Framework, if I remember right. You feel free to correct me if I'm wrong, where their laptops are designed to be repaired, upgraded, and everything's spelled out. They even put in extra screws with they're amazing products. They're more expensive, but that's the trade-off. And I think there is a mobile phone company kind of doing the same thing with a cell phone that's modular that you can repair and upgrade. Because that's one thing I do not agree with is disposable electronics. You have people complaining about not enough resources to go around, yet we're throwing hard to get stuff in the trash every day, like lithium ion batteries and disposable products like vapes. Come on. Really? You can't cry about the problem and add to it. Yeah. You can't create a problem and then add to it. It's like the people who complain about high gas prices, yet they're standing at the pump the next day pumping in their gas guzzling SUV. You can't have it both ways. I don't agree with that. So sorry for the tangent, but that's what I'm good for. I'm really good for tangents. So initial board power up testing. So again, we're going to limit it to 100 milliamps. That should be our best bet to keep things from getting fried. And yes, the red positive lead Okay, actually, no. Set the battery power supply. Ensure that the power output is disabled. Now, I'm going to bring up, again, it's much easier if I have examples to show you what I'm talking about when I bring things up. Again, I'm not endorsing any of these products, any of these companies. I don't get paid to endorse them. Not like I'd be opposed to, but I do have, you know, a lab that I've been working with. I have my own lab, my own workshop, and I've been stocking it up with products and equipment. So this is the little guy I've got. So 30 volts, 0 to 30 volts DC, up to 5 amps output. And it's programmable. If I really choose to, I can control it via UART interface. It's a good low-cost power supply. I've been using it for a while. But one of the features I wanted to bring in, it's got that on-off switch. So that enables and disables the power output. So you can have it connected. You can have all your voltage ranges, everything set up here. This has over voltage protection, which is your voltage limit, and over current protection, which is your current limiting. And you can set all that in these type of power supplies. This has been a really good power supply. Again, I'm not endorsed by this company. If and when that time ever comes, I will, you know, be open and upfront about it. But right now I am not. This is just what I use. And I'm just using it as an example to make it easier when I'm going through these videos so no one's left behind. So you want to make sure the output is disabled so that you're not accidentally powering the board when you're not ready to. Relative output to CN, I think it's 1, connector 1. Yeah, CN1, terminal 1. CN1, terminal 1, and the black oof output to CN1, terminal 2. So yeah, these power supplies are really good. They're really good to use. So if I just randomly talk about something different during these videos, it's because I'm responding to a chat in the Twitch stream as best as I can. So I'm sorry if it sounds kind of spastic if you're watching the video on YouTube. I get like that. I like to go on tangents. It's just me. So yeah, those power supplies are really nice. A lot easier to deal with than those old linear based power supplies. So the one like that I showed is built on a switching PWM system. The older ones, the older legacy power supplies are linear style. Well, yeah, they have current limiting, all that stuff. They weren't always the best, and they were easily damaged if you triggered the current limiting too many times. So the newer ones are definitely better. Even the lower cost ones are better. Now, I'm not saying I would turn down a higher end brand if a company wanted to sponsor me. I'm not saying that. Like, I'm just going to say Keysight, Agilent. I'm not going to say, you know, just to name a couple of names. I wouldn't turn down that equipment. But, you know, due to the cost and being a one-man team with a small budget, you know, I'm just going to put outward to be honest, you know, transparency. I'm married, you know, wife and I, we've got 5 cats. We have a house. So, you know, the income is just split between my hobbies and taking care of the living expenses. So what I'm allocating to these projects, you know, I'm cutting into things like my other hobbies. But electronics is not only my career, but is also my primary hobby. I've been doing this stuff ever since I was a teenager. One of the things is I used to be able to fix VCRs. I was fixing VCRs before I could drive a car. And, you know, so that's how long I've been into it, since I was like 12, 15. You know, I got into it early. I had a family member who was kind of dabbled into the hobby, and that's how I got interested in it. And I really liked it, and I stuck with it. So I got lucky that my career ended up being my hobby. So sometimes it's a hard time to tell when I'm actually working, because I just love to do it. So I got lucky. So test 44, we set the bench power supply. Like I said, 5 volts. Again, this is just smoke test. I don't expect anything too great. I'll put in observe the and check if the current limit became active. So basically, if you're yeah, so that's cool. Yeah, I got into fixing things too, and it's cool to do that, and I really appreciate running into other people who feel the same way I do about fixing stuff and working on stuff and getting into it since they were a kid. It's fun, and it's nice to run into others who've done the same, you know, have kind of followed the same path. So that's cool, man. Or, you know, whatever gender you are, I just say whatever. So let's see here. So enable. So we want to make sure if the current limit trips. That's probably a more appropriate term for this. So the current limit trip. Most power supplies, you'll hear it when the current. You'll hear it clicking, like a relay turning off. Something. Or you'll see an indicator on the power supply. Also, observe the PCB for any electro issues such as arcs or smoke. The magical blue smoke, that means the genie's being let out of a part. If any of the failure conditions arise, now for my new viewer, who I appreciate you checking us out. So this whole project, I've got it on YouTube. There might be a link in my stream information somewhere. So we're on episode 33 right now. And we've been following, the whole series has been following the idea of an electronic concept that started on a breadboard to an actual product that can be marketable. So what this is a stepper motor driver system built around an ESP32 as its main control interface. Oh, that's cool. You do YouTube too? You have to definitely drop me your channel. I'll subscribe. So it's built around an ESP32. Has RS-45 UART interface. So this is gonna be like kind of an open source dev kit project. So it'll be up to you to modify programming, do whatever you want with it, if you so choose to build it or buy the finished good from us. It's got 3 limit switch control switch inputs for like limit switches, or control inputs for like, and 3 control inputs for like buttons, switches, or whatever. It's got a standard USB UART interface for programming, like the standard ESP32. So it should be friendly with like the VS Code IDF. And then it's built around a Texas Instruments stepper driver chip, which I've been using in other projects and I really like. So it's something, so because I got tired of having to breadboard a stepper driver to play around, because I like working with automation equipment. That's one of the things I really like working with is automation equipment. So I got tired of breadboarding it. It's not really reliable. It's easy to mess something up. So I wanted something more permanent. I can just grab, start VS coding, throw some code on there, and experiment or start developing. That way I can build a bigger project off of it. So this would be the complete schematics. Everything's on GitHub, and you could download all my files. That's why I have this generic company logo here, mainly on the PCB to kind of show you, because I kind of go through how to do it, kind of teaching how to use KiCad. I've never used it before. I use for my main job, I use Altium Designer for the company I work for. And then for myself and my side projects, I use Altium Circuit Studio. So I've never used KiCad before, but since it's free, open source, free software package, I figured I'd do this series around that to help people who are interested in doing this type of work actually maybe have some foundation, some footing. But I'm also hooking in quality management systems, basically revolving around ISO 9001, because I have direct experience with that and I like QMS systems. So all this stuff I'm doing in VS Code, basically the markdown files, Excel files, it's all revolving around ISO and having proper quality management. So one of the reasons this test plan, basically the tests that we're going to be doing to the first board, first article inspection, first article test, is wordy, because my experience has been if you skimp out on stuff, any technician doing this type of work will find a way to shortcut it. So I like ISO. It gives it brokers no choice. If it tells you to do something, an employee can't say, I don't know how to do my job. Well, it's explained in these ISO procedures. It's explained in this work instruction. You can't come to me and say you don't know how to do your job. It's laid out here. That's why I like these systems. And it also gives you a path for, if you own a company, it gives you a path for, and I'm going to just be frank again, discipline, administrative discipline. If you've got policies and procedures in place, your employees have been trained on them, and they don't follow them willingly, it gives you a path for disciplinary action. Unfortunately, as much as I hate some things as much as other people, unfortunately, that's just the way life goes. Sometimes you have to deal with employees who refuse to follow their job. Disable the power supply output and inspect the for issues that could cause. Now, hopefully, since we did all the resistance measurements first, we shouldn't have a short condition where the power supply is freaking out. But there could be a design issue. 100 milliamps should be more than enough for an unloaded board for an ESP32 that has no programming. Because again, the ESP32 dev kits you buy that are pre-assembled with the breadboard legs and everything, the headers and stuff, they're typically flashed with firmware to basically light up the LED that's on the board. They're already flashed with firmware. But if you buy the raw SOMs, they're usually not flashed with anything. They're just sitting there waiting to be programmed. So they shouldn't really be doing anything to pull current. And your stepper driver is not going to try to do anything without, for one thing, a motor hooked up to it. Even if you told it to try to step or to try to drive a motor, it ain't going to do anything without a motor hooked up. It's not even going to try to draw current. So I wouldn't even, nothing should be tripping this 100 milliamps, not even the LEDs that are on there, because we only have 2 LEDs that should engage at this point, D1 and D2 for the 3.3 and the 5 volt power line, just basically power good indicators. The LED that is right here on IO4 Now, sometimes, depending on the default state of these pins, sometimes that'll be driven. Really depends. I've seen them do different things. So they'll sometimes this light will light up and there's nothing on there. So it really depends. So I don't know about IO4. I don't know if I've ever used it for an LED like this for a status indicator. So right now we'll just say it might light up. So it might light up. And even then we're only looking at what I'm driving about half current for half brightness. So at most 30 milliamps right there. So we're not really going to be drawing much. So again, that power supply should not be tripping. Cause these issues. Again, there's no reason to continue any of this testing if you've already got a failure condition here. Yeah, 100 milliamps should be more than enough. So if everything is good, so we need to put this into our Excel spreadsheet, test 44. I'll just go in here for the new viewer. So this is the test log for this. Again, we'll be doctoring this up because we're going to be tracking by serial numbers and stuff, but this is just to get the test log going. Does the pass the low power, low voltage and limited current test. All right. So just some basic, because that way we have test 44 over here and the test plan, test 44 here. So I'll drag this out of the way. I just wanted to kind of show for anybody new what I'm doing, mainly for the stream. All right, so that's our initial board power up testing for low voltage. If it passes this, now what we can do, disable the power supply output, set the 24 volt DC, and so we're going to kind of start small, 500 milliamps, because we're still not going to be connecting a stepper motor to this yet. For one thing, we don't have firmware to throw in here yet. We'll have to get to that through. It's going to be part of the testing, but this is all your basic testing. So basically, we want to, this device, while it'll work at 12 volts, which is perfectly fine because some stepper motors can handle 12 volts. The main intention is a lot of industrial automation equipment. 24 volts is the typical voltage for power and logic systems. So I want to make sure that we're at 24 volts at the output voltage, 24 DC, and the current limit 500 milliamps. That should be more than enough current to drive drive any of the subsystems other than hooking a motor up to it. All right. So we are going to be looking here, if we kick the voltage up to 24 volts and we get something, then we have a bigger problem. That something, doesn't like that 24 volts. And where that problem could be, even though our power supplies should be able to handle 32 volts input, we could have gotten bad parts. We could have gotten something wrong in. So, you know, if like these parts, the main buck regulators for the 5 volt and 3.3 volt, if they're a bad batch and something's wrong with them, they might not be able to handle 24 volts, even though they're rated up to 32 volts. And one of them could smoke, one of them could fry. So that could be an indicator of another problem. So again, you would do the same thing in a corporate, you know, company environment. Somebody else would like probably be handed the board. An engineer would be given the board to diagnose and see if there's a problem. Maybe have this part reworked if it smoked. Maybe with a new part from a new batch, maybe a different supplier, to see if it fails again. Because if it doesn't fail, that means you have a supply issue, and that has to be addressed accordingly. So that's why we're kind of doing these tests. So test 45 is basically does the power supply test the pass the operational voltage. Operational voltage. So 24 volts is going to be considered the operational voltage for this power supply. Okay, so if it passes that, so we can assume then that power supplies are good. And now we'll want to actually check the voltage coming out of these guys. We want to make sure, because again, yes, we will eventually test reverse voltage connection here, but that is not the strategy for this. This is our first pilot board. We're just kind of testing basic functionality, kind of doing some very basic things. So we want to check the voltage coming out of the that's 46. With the power supply output enabled, set a figure a multimeter to DC and connect the negative lead to TP. All right, so let's find a test point. So right here, TP3. TP3, ground, and the lead to TP1, which is 3.3 volts. Check. Is 3 volt plus or minus. So we want to give it a little bit of a tolerance, because most voltage supplies are. We will give it a tolerance of 125 milliamps or millivolts. Plus or minus 125 millivolts. So what that would mean, because I'm horrible with math in my head, so it could be 3.3 minus 0.125. So it could be 3.175. Helps if I or 3.425. That's to allow for a tolerance in the power supply. And most electronic components are going to be tolerant of that little slop. It's not too big, it's not too great. because when you're dealing with components like this, your main chip's going to have its own tolerance that it's going to try to maintain, but it's also dependent on the boost chip, the inductor, and what comes back on the feedback line. So it uses this feedback line to help regulate what it's putting out. And the boost chip, I can't remember the primary function, but definitely the inductor, its tolerance for the inductance it has can affect everything, the switch cycles. So you're going to have some variation in your output voltage. It's not going to usually be complete, 3.3 volts right on the nose. There's too many factors that are involved stray capacitance, stray resistance, anything could be pulling it, because you're also already kind of loading it down with this 3.3 LED. You're kind of pulling it down just a hair, not a whole lot, but you're not going to be 3.3. That's why you need to allow for a tolerance in here. 125 millivolts might be a huge range, might be more than necessary, but we'll allocate the slop, that much sway in this, that much change. All right. Again, we're going to copy this. If any failure condition arise. So that's going to be test 46 in our documentation. Okay. Does the 3.3 volt power supply output the voltage? Okay. Proper voltage within tolerance. And again, if it's not, you need to stop and continue, because other tests, or stop, check, elevate, whatever, and stop testing. Because again, if your 3.3 is not the right voltage and you can't figure out why, it's pointless to do the other testing, because if you're not feeding the ESP32 with enough voltage or enough current, it will not operate properly, and other tests may not work properly. Then you're also could be causing problems when you start actually using the limit switches. You could pull it down even more, which could put the ESP32 in a brownout state. So yeah, we definitely want to make sure that we're functional at each one of these stages to make sure that you can continue on. So now, if that succeeds, 47, we're going to go to the 5 volt. And back to the power supply. 5 volt, which is TP2. Zero voltage output is positive. 5 volt, same tolerance. So another test. Does a 5 volt. All right. So right now, the device is in an unloaded stage. So nothing's really pulling current other than a couple of LEDs. The ESP32 is in kind of like a standby gray state, doesn't know what it's doing. It's just kind of chilling. Again, that LED might be on, might be pulling current, no biggie. RS-45 transceiver is just kind of sitting idle, not really doing anything because you're not driving it or receiving from it. Limit switches, those optos aren't triggering because there's no inputs to them. The UART is just kind of chilling. So everything most components have a slight current drain just sitting there in idle state, but we're talking microamps. You're not talking a huge voltage drop or anything. You're talking microamp current pull, just sitting idle. Some components, shut down, don't really do anything. They're just sitting there, just kind of dumb until something tells them to do something, till they receive an input. But right now, we're basically on what's called an unloaded state in our power supplies. So one of the things we probably should check for is voltage ripple on these outputs. I'll have to look at some specifications and dig up some stuff because it's going to be a little bit more of a complicated test to set up. But we will need an oscilloscope for that. And so I have one, which is kind of cool, the one that I have. Again, the same thing about endorsements. I'm not paid, I just have one of these. So I have one of the more basic 2000 series picoscopes. I got one of the older ones, which is more than enough for what I've been needing it for, because for now, I plan on buying a bigger scope. But the great thing about the picoscope is it's basically your front end interface hardware, and then it ties to the computer through a USB port, and the computer becomes the display and handles all the measurements, all the math. So it becomes the brains of the oscilloscope, whereas this is just the front end, your scope probes. So I've got one of these. So it's going to make it a lot easier for doing these videos, because then I can just share the screen and show you. So we'll be setting up one of these to do to check the voltage ripple. Again, I'm going to look over the data sheets, kind of see what their expected ripple are, and kind of pull that in on my own time. That way I don't bore everybody with the specifics, because there's going to be a lot involved, or there might be. Plus, we're also running out of time. I don't want to run these videos any longer than an hour if I don't have to. Sometimes I will if I'm in the middle of something, or I just want to tidy something up. But we've got plenty of time while we wait for PCBs to arrive before we can even build a board to do any of these testing to, so we might as well get all this done. So the next video will be tomorrow at 2 p.m. and we'll pick up where we left off. I should have everything set aside so we can write up the tests for power supply ripple, for the unloaded ripple. And we might actually test loaded ripple, which won't really be any kind of ripple in the power supplies, because the 3.3 and the 5 volt don't really power anything too intensive. The stepper motor will be driven from the 24 volt directly. Well, it'll be through the stepper driver chip. So we're not really loading anything down. So the unloaded ripple would probably be more than sufficient test. Maybe we'll also kind of write in the test, do some basic thermal measurements with the IR temperature probe, just non-contact temperatures. Just kind of see if there's any kind of temperature rise around the power supply while it sits idle after like 20 minutes, just to kind of check. Maybe we'll do some loading to the power supplies. I've got some power resistors, and we can kind of figure out maybe like a 1 amp load and how to tie it in, and just kind of make sure. But that'll be leading more towards possible destructive testing, and I don't want to do any destructive testing until we can actually build up like maybe a second or third board. So the pilot board is basically just to make sure that it's okay to use parts to build up other boards to do further, possibly destructive testing. And then we'll just continue expanding the test plan after that. So we're going to be bouncing back and forth between, at that point, between building boards and doing additional testing for this major test plan. And then once we're through all this, the major test plan's done, everything seems to pass, then we'll start planning the next steps. One of them will be devising a manufacturing test plan, basically a production test, which will be really short and sweet, run you through. We're going to be doing some firmware development together. So that's going to be a lot of fun. So there's a lot to do. So again, I expect this particular video series to go on for quite a while longer, maybe even till the end of next year. It really depends. There's a lot of ground to cover. There's a lot you have to do before you can before you're ready to put a product on the market. And I don't intend on being one of those fly-by-night companies. I want to do quality and put something out there that is usable and that I'm proud of, and that I'm happy to build and people to be using. I don't want to just put slop out there on these online stores and with these weird company names and that you can never buy from again, and you can never get traceability or accountability from them for crappy production. I don't want to do that. So if this takes us till the end of next year to put on the market, it'll take till the end of next year to put on the market. But I thank everybody for viewing and checking us out and checking these videos out. I'll be pushing all these updates to the GitHub, all the changes, all the new files, everything to the GitHub. So if you're following along by downloading, you can basically do an update to your files and have the latest changes, all the new documentation additions and stuff. So thank you for watching. Have a great rest of your afternoon, and hopefully catch you tomorrow.